Welcome to this episode. I'm Mira.
Hi everyone, I'm Jensen. Great to have you with us.
Today we're discussing the article titled LoRA Plus, Efficient Low-Rank Adaptation of Large Models.
So, state-of-the-art deep learning models are pretty massive and costly to pre-train, right? While we can access these models through APIs or open source platforms, adapting them for specific tasks is a whole different story. Full fine-tuning isn't really feasible due to computational costs. That's where resource-efficient fine-tuning methods come in, like prompt tuning, adapters, IA3, and LoRA. LoRA, in particular, uses a low-rank matrix adapter to cut down on trainable parameters, which helps reduce training costs while keeping performance intact. But using LoRA efficiently means picking the right hyperparameters, especially the rank and learning rate. All right, Mira, could you tell us more about the related work and contributions mentioned in the paper?
Sure thing. Detmers et al. Introduced QLoRA, which is a quantized version of LoRA that cuts down computation costs by quantizing pre-trained weights. Lee et al. Came up with LoftQ for better initialization in quantized training. Then there's Vera, which freezes random weight-tied adapters and learns vector scalings, further reducing trainable parameters. The paper focuses on setting the LoRA learning rate, providing guidelines through a theory of scaling for neural networks. It proposes LoRA++, a method that sets different learning rates for LoRA modules A and B, improving feature learning in low-rank adaptation. This theory is backed by empirical results across various language models and tasks.
Great insights. Now let's explore the setup and definitions. What foundational elements does the paper outline for its methodology?
Well, the paper outlines a model-agnostic setup applicable to general neural network models. It considers a neural network with input X, network depth L, layer mappings, hidden weights, and input-output embedding weights. The model is pre-trained on a dataset for tasks like next token prediction and can be fine-tuned using methods like LoRA, which reduces computational cost by employing low-rank weight matrices.
Interesting. Could you explain how LoRA works as defined by Hu et al. 2021?
Oh, absolutely. LoRA constrains the update of any weight matrix W in the pre-trained model during fine-tuning by representing it with a low-rank decomposition. It's expressed as W equals W equals W of AFMAR R BA, where B and A are trainable matrices, R is a rank much less than min1 n2, and alpha is a tunable constant.
Got it. And what about the scaling of neural networks? How does that play into this?
Right, so the paper discusses adapting the network initialization scheme and learning process as the width grows to avoid numerical instabilities. It suggests scaling the variance of initialization weights as 1n to prevent large pre-activations. This involves analyzing statistical properties as n increases and adjusting parameters like initialization, learning rate, and architecture to achieve desired properties in the limit.
Thanks for clarifying that. Moving on. Could you give us an intuitive analysis of LoRA? What's the reasoning behind setting different learning rates for matrices A and B?
Sure. The section explores the intuition behind setting different learning rates for matrices A and B, especially as model width increases. It looks at training dynamics when the width approaches infinity, using a linear toy model to analyze pre-trained weights and LoRA weights.
That's noteworthy. Can you tell us more about the initialization schemes proposed in this analysis?
Oh, definitely. Weights are initialized using Gaussian distribution. For LoRA, the product Bt should start at 0, implying one weight. Two schemes are proposed. Init1 with sembutter B equals 0 and echo minus 1, and init2 equal tuft 1, say 2 equals 0.
I see. And how does the learning rate factor into this analysis?
Good question. The learning rate I is analyzed under the assumption W equals 0. The update in model output is driven by three terms, with the first two being linear contributions and the third a multiplicative update. Efficient feature learning requires both delta T1 and delta T2 to be theta 1.
Thanks for breaking that down. Now, let's talk about stability and feature learning with LoRA in the infinite width limit. What does the paper say about this?
Well, the paper extends previous analysis to general neural architectures with LoRA layers, showing that using the same learning rate for both A and B leads to suboptimal feature learning when model width is large. This issue can be resolved by setting different learning rates for A and B.
That's interesting. How do they define stability and efficient learning in this context?
Oh, sure, stability is defined as having ZB equals O1 as n goes to infinity, ensuring no explosion of quantities as width grows. Efficient learning involves both A and B being sufficiently updated to induce changes in feature directions and weights.
Thanks for explaining that. Finally, let's discuss the experiments with language models. What were the key findings from these experiments?
The experiments showed that test accuracy is maximal when phi-A, especially for harder tasks like MNLI and QQP. They identified a default value for the ratio MELANT that generally improves performance compared to standard LoRA.
That's great to know. How did RobertaBase and GPT-2 perform in these experiments?
Yeah, RobertaBase was fine-tuned with =R=8, trained with half precision, and showed maximal test accuracy for learning rates where RIBA. GPT-2 also achieved maximal test accuracies with similar learning rates, with a larger gap for harder tasks.
And what about Llama? How did it validate the theoretical findings?
Llama 7B was fine-tuned on MNLI and FLAN v2 datasets using LoRA, showing advantages of setting WB with a 1.3% gain on the MMLU benchmark. For MNLI was nearly optimal, consistent with the idea that efficient feature learning isn't needed for easy tasks.
Wow, that's quite impressive. The results really highlight the importance of setting the right learning rates.
Jensen, what's your overall take from this article? There are so many points to consider.
Well, I think the paper provides a solid framework for understanding and optimizing LoRa's efficiency. The emphasis on different learning rates for A and B is crucial, and the experimental validation really backs up the theoretical claims. It's a significant step forward in making large models more adaptable and cost-effective.
Thanks for joining us today. Until next time, take care.
Goodbye, everyone. Remember, if your friends share an article with you, listen to a summary of it before committing to the full article by simply forwarding it to summary@lettercast.ai.